2.4, polynomials and their real zeros. A rational zero theorem application is that we use it to discover what the possible rational zeros of a function are. This was very, very applicable when we didn't have graphing calculators to quickly and easily tell us what the zeros of something were. And it is a little bit outdated because of that, but it is still really useful in order to find rational zeros when you can't graph for whatever reason. So the first thing we look at is what we call P and Q. Okay, P is a factor of the constant term and Q is a factor of the leading coefficient. So what I mean are this 6 and this negative 15. So specifically, the P is 15 because P is always a factor of the constant term, meaning that the P's are 1, 3, 5, and 15. Now, Q is going to be any factors of that 6. So those choices are 1, 2, 3, and 6. And we find the possible rational zeros by saying all of the possibles of these come in some form of plus or minus P over Q. So the way I like to organize my thinking here is I like to take my first P, which is 1, and put it over every single one of the Q options. We also need to consider that we could have 3, which is the second P factor, over every single one of those, as well as 5 over 1, 2, 3, and 6 also, as well as 15 over 1, 2, 3, and 6. Okay. It is important to note here that some of these reduce, and you do not need to list them more than once. I want you guys to recognize that 3 over 3 is the same thing as 1 over 1. It's just 1. You don't need to list that one again. 3 over 6 is the same as 1/2. We have also already listed that. We don't need it again. Other ones that reduce, 15 over 3 will give us a 5, which of course we have already listed with 5 over 1. And then 15 over 6 would be 3 over 2, which again we have already listed. So we can get rid of that one also. Let me just double check for any others. I think that's all of them. So ultimately our list will end up being plus or minus 1, plus or minus 1/2, plus or minus 1/3, plus or minus 1/6, plus or minus 3, plus or minus 3/2, plus or minus 5, plus or minus 5/2, plus or minus 5/3, plus or minus 5/6, plus or minus 15, and plus or minus 15/2. Now, I know that that is long, and a lot of my students have asked, well, can I just put plus or minus at the beginning? And the answer is no. You need to write it for every single term. This is something that SLCC requires. I have been told explicitly that you do need to list the plus or minus and every single one of these. So just a heads up for you there. Okay, again, why is this useful? Well, because sometimes we have things that we don't really know how to graph. I don't know how to graph an x to the 4th function. So to be able to find the zeros, I need some other form. So here's what we do. We find all of our P and Q values. Okay, so for our P being 16, we get 1, 2, 4, 8, and 16. For our Q being 1, well, that's just 1. 1 is the only factor of 1, which actually makes this really easy because that means our choices are 1, 2, 4, 8, and 16, plus or minus on both of those. So with that, we can test out to see if any of these are going to divide evenly. Okay? So in order to check if 1 is a 0, we can do it this way, and we can check to see, hey, do I get a 0 remainder? Well, we'd drop the 1, multiply by 1, add down, take that 8, multiply by 1, put it there, add down, that's 20, multiply, add down, multiply, add down. And we do get a 0 remainder. Another fun thing you could have done, the definition of a 0 is that this is all going to equal 0 when you plug it in. So you can actually just check. You can, by plugging in, and f of -1 actually comes out to be -10. Okay, f of 2 comes out to be 96, and f of negative 2 comes out to be 0. So, and I just did kind of the first couple here, just to see what would come out. I also want you to notice, though, so I tried 1, we got a 0 remainder. That would leave us with this x to the third plus 8x squared plus 20x plus 16. Okay, well, if 1 worked the first time, we could try it again, see if it works again. It's not going to, just so you know. But I was looking for a list of other ones that would work, and I know that negative 2 is going to work. So let's go ahead and synthetically divide out there. Perfect. This is going to leave us with x squared plus 6x plus 8. Now, this is really useful because I know how to factor x squared plus 6x plus 8. That factors to x plus 4 times by x plus 2. So the answer to what are my zeros, 0, 1, negative 2, oh, nope, not 0, I apologize, 1, negative 2, negative 4. There's something missing here, though. I want to just write out in full form what this polynomial is equivalent to. So hopefully you guys can grab this idea here. There should be 4, and in fact there are. It's just that the negative 2 has a multiplicity of 2. So I hope that helps. You guys picture that yes, there are only 3, but one of them has a multiplicity of 2. Okay, let's go ahead and move on to this one now. So this one very clearly has a greatest common factor of x squared. So let's pull that out. That leaves us with 3x squared plus x minus 9. Still all equal to 0 because that's the whole point of what we're doing. So x squared set equal to 0 is really easy. Like, that is very obviously a 0 with a multiplicity of 2 there. But this other piece, the first thing I would try to do is to try and factor. But then I'm looking at this and I'm like, 3 times negative 9, well, that's negative 27. The only factors of negative 27 are 1, 3, 9, and 27. None of those are only 1 apart to give me that 1 for my b value. So I'm going to go ahead and try and do quadratic formula instead. So this is what your quadratic formula would be. It's the opposite of b plus or minus the square root of b squared minus 4 times a times c all over 2 times a. Okay, well, that simplifies down to this. So 4 times 3 times 9, we make it positive because a negative times a positive times a negative comes out positive. And we get this. And the square root of 109 doesn't break down at all. It's just stuck there. So those are our other 2. So keep in mind, this one does indeed have a multiplicity of 2. And then the other 2 come from, one is the plus version, one is the minus version, which does add up to 4, which is how many we should have. For this next example, it actually wants us to go ahead and graph this one by hand. And in order to do that, we need to know some things. Specifically, we're definitely going to need some x-intercepts here. So in order to do that, we are going to go ahead and find all of our possible rational zeros. So we need our p, which is 8. And our factors, therefore, are 1, 2, 4, and 8. We also need our q, which in this case is just 1, which means its only factor is 1, which is very convenient. So our possible rational zeros are plus or minus 1, plus or minus 2, plus or minus 4, and plus or minus 8. I like to start with 1 whenever possible. It just makes everything a lot easier. So we're going to go ahead and synthetically divide 1 into there. So remember, these are just your coefficients. 1, negative 2, negative 7, 16, and negative 8. So drop the 1 down, multiply by 1, add down, multiply, add down, multiply, add down, multiply, add down. Perfect, we got a 0. That's great. Well, now that leaves us with x to the third minus x squared minus 8x plus 8. And I am looking at that going, I can factor by grouping here. I can do a GCF of the first group as x squared times by x minus 1. So again, I'm just looking at this group and recognizing that they both have an x squared to them. And it leaves us with x minus 1 there. And then I can also pull out a negative 8 here so that this will match. Okay, the whole point is so that they match. We pull back out. So x squared minus 8 and x minus 1 are what this one factor to. So x minus 1 is actually a multiplicity of 2 factor because it came out here and it came out here. So because I got it in both places, that gives me that multiplicity of 2. And then I also have x squared minus 8. And the whole point here is to find zeros. So we have it set equal to 0. Okay, so then that means that on this one, it's going to be x equals 1. On this other factor, it's going to be x squared equals 8, which leaves us with x equaling plus or minus the square root of 8, which can be simplified to plus or minus 2 root 2. Okay, so our x-intercepts are at 1, negative 2 root 2, and 2 root 2. If you left that as the square root of 8 and negative square root of 8, that's fine. Our y-intercept is, of course, at negative 8. I can just grab that straight from the beginning. And then our end behavior, I'm seeing this is a positive 1 with a to the 4th degree here. So that's going to give us even positive, which, of course, both go up. Okay. Then all we have left to do is actually put these things on the graph. So let's start by doing our x-intercepts. Now, I don't know exactly what the square root of 8 is, but I do know that it's just a little bit less than the square root of 9. The square root of 9 is 3. So we've got to be just a little bit less than that. So negative 2 point, I don't know, almost 3. And 2 point, I don't know, almost 3. And then we've got our 0 at 1 still. So we put those on there. Then I'm also going to go ahead and put that y-intercept on there. And now, knowing what our end behavior has to look like, I'm going to start on the right side, which is actually kind of odd. Most people would start on the left side. But this is what it ends up being. So, well, actually, let's go ahead and start on the left. It'll make more sense from the left. So I know I have to be going up here. So, all right, I got to come down and I have to hit this. And I don't know a whole lot about this other than that its multiplicity is 1. So I guess it's just going to go straight on through. And I know I got to come down here and hit this y-intercept. So it's got to come up here. And then I'm coming back up here towards 1, but I know that 1 has a multiplicity of 2 in this case. So it's going to bounce right on off. Okay, and then at some point, I've got to turn back around because I have to go through this point for that intercept, and I also have to go back up for my end behavior. So again, we're really just connecting dots here, guys. We're going, oh, there's the arrow, there's the dot, there's that dot. Oh, but this dot does something weird and makes it bounce, but I still have to come up and connect that dot and connect up there. So there's that graph, give or take. I don't know exactly how big those little divots are. I really don't know. But something like that is what that polynomial should look like when it's graphed. Okay, next example here, it just wants me to find the zeros and their multiplicity. Well, let's see what our possibles are. Our p is 3 and our q is 1. So we only have 2 choices here, plus or minus 1, plus or minus 3. So I always like to start with a 1 and see. Let's see what happens. So we get our 1 there, multiply, get a 3, and we add, we multiply, and then add down and get that negative 1. And then negative 1 times 1 gives us that negative 1. We add down again, then we multiply, and then we add down again. And we did get a 0 remainder, so that's super helpful. This one is now just x to the 3rd plus 3x squared minus x minus 3, which you actually probably could have gone ahead and tried to factor if you wanted to. But what I was like, you know what? I wonder if 1 has a multiplicity of 2 again. Let's see. So let's try it again. Let's try to put 1 into it again with synthetic division and see what happens. So we drop our 1, multiply by 1, add down. Multiply by 1, add down. Multiply by 1, add down. Hey, look at that. That's useful. So we have a factor of x minus 1 squared with our multiplicity of 2. And again, part of that is just Mrs. Boyce being experienced with trying these out. But I often like to try 1 twice just to see if it has multiplicity. And if it works twice, that's a good sign. The other thing here is that now this 1, 4, and 3 give me an x squared plus 4x plus 3. And I am pretty quickly recognizing that pattern of, hey, wait a second, 1 times 3 is 3. 1 plus 3 is 4. So when I see a 1, a 4, and a 3, and I'm automatically thinking, ooh, that's factorable. So I know that that's going to factor to x plus 3 and x plus 1. And would you look at that? That's 4 with all of our different multiplicities, because we've got 2 here, 1 here, and 1 here, which is how many we should have. So easy enough here. x equals 1 is a 0, x equals negative 3 is a 0, and x equals negative 1 is a 0. Again, x equals 1 does have a multiplicity of 2, but x equals negative 3 and x equals negative 1 both have a multiplicity of just negative 1. Okay? All right, last example for this section is to find the real solutions of 5x squared plus 2 equals 3x to the fourth. So whenever we're finding solutions are the same thing as zeros. So I'm going to want to set everything equal to 0. In order to do that, I need to move that negative 3, or that 3x to the fourth over, and I do it by subtracting. So that gives me this, negative 3x to the fourth plus 5x squared plus 2 equals 0. Now, I don't know how to factor x to the fourths, but I do know how to factor x squareds. And I'm recognizing that this is an x to the fourth and this is an x squared. Well, if I say like, okay, so x squared is u, then u squared is x to the fourth. This is what we call u substitution, if you guys remember this. So we're going to have negative 3u squared plus 5u plus 2. So again, I don't know how to factor things with to the fourths, but I do know how to factor things with to the seconds. So we're going to put our negative 6 on the top of our x and our 5 on the bottom. Negative 6 came from negative 3 times 2. And I'm recognizing that that's going to give us a negative 1 and a 6. Of course, I always do this with a times the variable on the top. And you guys are about to find out why I do that right now. That reduces to negative 1u over 2. 3/6 is 1/2. This one actually also reduces, which I think is kind of fun because the negatives cancel out. So this one's actually 3u over 1. And so then we take that 3u plus 1 and we multiply by negative u plus 2. And it still all needs to be equal to 0. Okay? Well, u doesn't do me a lot of good at this point, so I would actually plug in x squared at this point again. So I would say, oh, just kidding, I don't actually like u. U didn't actually have anything to do with my original problem. Let's put our x squared back in. So now we've got negative x squared plus 2 multiplied by 3x squared plus 1, still equal to 0. So let's go ahead and split them up. Negative x squared plus 2 equals 0. Well, that means negative x squared equals negative 2. That means x equals plus or minus the square root of 2. Easy enough. So then for 3x squared plus 1 equals 0, well, that means 3x squared equals negative 1. And that x squared equals negative 1/3. Some of you have already figured out that we have a problem here. That would mean that x is equivalent to plus or minus the square root of negative 1/3. But we can't take an even root of a negative number. The two real solutions, they're not rational, but they are real, are plus and minus root 2. The other two solutions, whatever they are non-real. At this point, we don't need to worry about that. We just need to say, I don't know, these are the two real ones, the other two must be complex or non-real.